Let's consider this particle hanging on a string. We want to know, when we release it from this position here, what's the speed when it reaches a position here at the lowest point of the arc? Let's use conservation of energy to do this. We'll start by knowing that we release it from this initial position, which I'll call position 0, at rest from velocity equals 0. Then when it passes through this position here that we'll call position 1, it will have some velocity, v1. We can try and conserve energy and see how far we get. To do so, we have to ignore friction. So say there's no friction, ignore aerodynamic drag, and that lets us conserve mechanical energy between these two, which means E at point 0 is equal to E1. I'll go ahead and write a more complete version of this. There's no spring, so I'm going to leave out the spring term, and we'll just include the kinetic terms, 1/2 mv squareds, and the gravitational terms, mgy's. We run into an issue here. We can get rid of this one, because my initial velocity is 0, and we can set my y equals 0 wherever we'd like. So I'm going to go ahead and set this y0 is equal to 0 to get rid of that one. But in order to solve for v1 as our unknown, we're going to need to know y1, which we don't know yet. We have to do a little bit of geometry to do that. I think it's doable. Shouldn't be insurmountable. Let's do this geometry here. We have 1 meter length of string. When it swings through the bottom here, that means that this will also be a meter at this point. And we want the difference between the meter there and whatever the vertical height was over here. So we'll consider this right triangle and see if we can get that length. I think we can. We have an adjacent side here, 30 degrees, touching our adjacent side. So cosine will project that 1 meter length onto that side, or we can call this 1 meter times cosine of 30 degrees. That will give us the length down to there, which lets us say that this height here will end up being 1 meter minus that 1 meter times cosine of 30. And I've left myself without room to write that. I will write it down here. So this height here is equal to 1 meter minus 1 meter times cosine of 30 degrees. Or I might actually be inclined to write that as 1 meter times 1 minus cosine 30 degrees. We can do this. That gives me a height of 0.13397 meters. And in my coordinate system now, that means that my y1 position is a negative of that, right? Because this is a distance below. So my y1 is equal to negative 0.13397 meters. Apologies if this got a little bit crowded here, but you get it now. So now we know y1. We can luckily cancel out this mass by dividing both things by the mass. And I'm going to rewrite this. Here, 0 is equal to 1/2 v1 squared plus gy1. Solve one equation, one unknown. For the unknown we want to know, v1, by moving the gy1 to the other side, so we get negative gy1. Yeah, we can do additional steps here. We have room on the screen. And then multiplying by 2 and taking the square root of both sides. Luckily, y1 is a negative, so the negatives cancel. Otherwise, taking the square root of a negative there would be a little bit tricky. Oh, I left out the 2. We have to multiply by the 2. Here we have the 2, 9.8 meters per second squared. And my y1 was the negative 0.13397. Honestly, I probably could have rounded that a little bit. I just didn't want to introduce round off error. At the end, though, we will round our final result to a reasonable precision of 1.62 meters per second. This is a velocity, so we will report it with the magnitude and a direction. If you actually do this experiment, you might have some drag that matters. You might have some friction here. Things might not be perfectly rigid, and so if other things are moving, some of the energy might end up going into places that we didn't account for here. But I would expect that you would be pretty close to this if you set up your experiment so that it follows the assumptions that we made in doing this calculation.